Oh, good morning to the northwestern hemisphere, and good evening to the rest of you. This is Orbit at a Tilt. I forgot to put my little frame up. Let's do that. Here we go. This is Orbit at a Tilt. I'm Adam Tilted, your dizzy dude, and this is the show about space and science. I do my best to break down what's going on in the universe into easy to understand and fun segments. And today, I'm really excited about today's topic. Today we're going to be talking about a very important experiment that happened on this day in 1919. But first, I want to show you a couple of skywatching events that are going to be happening this week. Let me switch over. All right, this is the sky right now from Houston. So we're looking at Thursday. So I'm going to move this ahead to Thursday. Which is the 31st. And let's move this ahead till nighttime. Okay. So this is 10 o'clock. And if we look over, notice that we can still see Venus, which is awesome. I love it. This is the highest that Venus has been in the sky for a long time. So I love going out there and seeing Venus. I mean, you can't miss it. But over here towards the east, we're going to have another fun thing. Notice Jupiter. You can't see that, huh? Hold on. Can you see that now? No. Okay. Well, anyway, there we go. Jupiter, right there. Okay. If I move time forward a little bit, then you'll see that the Moon and Saturn are very close to each other. And then Mars comes behind them a little bit later. So that should be a pretty cool sight, the Moon and Saturn. The Moon at that point is going to be a waning gibbous just past full moon, which happens today. Good morning, Amy. How are you? Thanks for stopping by. So this Thursday will not be a good day to look at Saturn through a telescope because it's so close to the moon, and the light from the moon will wash it out. But it will look pretty to the naked eye, and it's a good way for you to know where Saturn is in the sky. On Thursday, it'll be right next to the moon. And this is also true in the southern hemisphere. You guys will also see the moon and Saturn rise together in the evening on Thursday. Yes. I get confused whether you're a day before or a day behind, but you are a day ahead. Okay. The other thing is on Sunday. I'm going to move this ahead to Sunday, which is the 3rd. And the moon is right next to Mars on Sunday. So that's another neat pairing. Now, by that time, the moon will be getting pretty close to third quarter. So it's getting to be a better time to look at the moon through a telescope because it's got a good portion of it lit that you can see, but it's not so bright that it's going to wash it out. Okay, so that's what we've got going on. Let's see, did I catch anything, miss anything? On Saturday, the moon is at apogee. Bonus points. Anybody know what that is? What does apogee mean? Put it in the comments and we'll see if you're right. Okay, so this experiment in 1919. First off, we'll go back a little further than 1919. And Let me see if I can get my cute little... I made some little sketches of my own that I'm going to use to talk about this. Okay, so there was Newton, Sir Isaac Newton. You know, he's the one that saw the apple fall from the tree, supposedly. That's kind of a simplified version of what really happened. But Newton observed this behavior, the apple falling to the ground, and he developed a theory about gravity. And sorry, Bob, I'm not a good astrologist, so I would not be able to help you with that. I do know some people, though, so catch me later. Now, if you want to know where Jupiter is going to be in a couple weeks, I can tell you that. All right, so Newton decided... Hi, Danica. Thanks for coming. Newton decided that gravity is a force that causes massive objects to pull less massive objects towards them. So what he observed with the apple is that the Earth is more massive, therefore it has more gravity, and it's pulling the less massive apple towards it. Hello, Bob. Okay, so for a long time, that was the prevailing theory. That was the theory that everyone accepted was the truth. And that theory is very useful as a way to think about things simply. However, when things get bigger, when you start to look at things like the solar system, and you start to apply Newton's laws, they don't really work that well. So, along came Einstein. Einstein says, well, okay, so you see this apple falling to the earth. How do you know that it's not the earth moving up to the apple? How do you know? He says gravity doesn't exist. Because from the apple's point of view, it's not going anywhere, and the earth is zooming up towards it. So, it's all relative. The theory of relativity. You see where we're going with this? Okay, so you have probably seen... I'm going to add a little prop here. You've probably seen some comparisons like, if you think of a trampoline and, you know, you put a bowling ball in the middle, it causes the trampoline to go down, right? That is a visual representation of what Einstein was saying, is maybe there's no such thing as gravity. Maybe objects in space curve space-time. And if space-time is curved, then as far as the Earth is concerned, it's traveling in a straight line. But relative to the sun, it's traveling in a circle. But that's because the sun has curved the space. Right? Okay. Now, this involves a lot of complicated geometry. And I'm not going to go through all the geometry that's involved to come to these conclusions. However, if you do want to learn more about that, I will put a link in the comments. I meant to put it in the description. I'll put a link in the comments to a series of videos on YouTube by PBS that does a great job of explaining this in more detail. All right, so I want you to think about this. This is one of Jake's toys. All right, imagine that there's an ant on top of here, and the ant is walking, and it walks. Pretend that this is not a cave. Okay, it walks all the way around. Is the ant walking in a circle or in a straight line? What do you think? It walks all the way around. Is that a circle or is that a straight line? That was what Einstein was wondering. What do you think? It's all relative. That's right. Now, from the ant's point of view, it's walking in a straight line. It doesn't, for its purposes, this, wherever it is on the sphere, may as well be a flat plane that is just tangent to this sphere. Tangent means that it intersects at one point. So this would be, wherever this touches, whatever point that is, that's the tangent. Okay? So wherever the ant is on there, for that moment, he can assume that he's on a plane instead of a sphere, and Newtonian physics will work just fine. Okay, let's see some of these. Yes, it's all relative. If two apples are falling at a different time, how do the earth and the two apples interact? Do they interact? And how do you know there are two apples, Bob? And how do you know that they don't interact? So, yeah, that's where this gets all really trippy, because we're not used to thinking in 4 dimensions. We have 3D dimensions, but we don't observe time. I mean, we observe the passage of time, and we've attached some meaning to that, but time as an aspect of space-time, we can't see. Now, one thing that is important to understand, and I meant to say this at the beginning, when we say something like the theory of relativity, that's not the same thing as saying, oh, I have a theory about that. Scientists use the word theory in a different way. In science, a theory is a proposition that is based on observations and is waiting to be proved false. So Newton had a theory of gravity, and it was based on good observations, the best that anyone could do at that time. Einstein had a theory, and his theory was not based on observations, but was based on math. Now, math is a constant. 2 plus 2 is always 4. Always. No matter what you call it. Dosi, quattro. It doesn't matter what you name it, what you call it. That idea is true everywhere in the universe as far as we know. So, it should be true that we can take math, like geometry, and make some predictions about how the universe will react. And that's what Einstein did with his theory of relativity. One of the things that Einstein predicted would happen as a result of space-time curving. Oh, Dana, this is a good question. They were actually peers. They fought it a lot. I mean, hold on. Let me look that up, because I may have just lied. That's a good question. I'll find out. Okay, so now Einstein was a nobody when he came up with this. Nobody really paid him any attention. Newton was firmly accepted as that's the way it is. And Einstein didn't have any proof. All he had was math. And it's hard to, thanks Bob, 200 years. It's hard to get people to believe just math, especially when he's using math as complicated as he was. So this theory was out there, and some scientists were like, what kind of experiment could we do? So if Einstein is correct, then a massive object will curve space-time around it. And we should be able to observe that curve from light that's behind this object. When it encounters the space, it will curve. And the result of a curvature of light is magnification or a distortion of of the view. And the largest object in the solar system is the sun. But the problem is, there's this big, you can't see the edge of the sun. It's too bright. It gets all faded away. But if we could see the edge of the sun, then we could see if Einstein was right. So, along came the eclipse of 1919. And I'm just going to illustrate what happened there. And I got some more drawings. Let me know if you like these drawing things or not, because this is a new thing I'm playing with. And the camera's all backwards. Sure. All right. So I'm going to use this magnifying glass with the middle blocked out, okay, to represent the sun at eclipse. And I want you to see what happens as the sun moves across this field of stars. You see how it's distorting it, right? Distorting behind it. Now, there was an eclipse in 1919 that lasted for, the totality lasted for 6 hours, which was amazing because they were able to take a lot of observations. The Royal Academy of Scientists sent out 2 groups, one to an island off the coast of the west coast of Africa and another one to Brazil. And they made these observations of the sun, which happened to be in front of the Hyades cluster at the time of the eclipse. So they took a picture of the cluster during the eclipse and then compared it to pictures after the eclipse or before the eclipse, and the stars were 6 minutes, sorry, not 6 hours. And Bob, I think you're right, they did it in Australia as well. So they were able to see that the relative positions of the stars in that star cluster changed when seen through the edge of the sun. And that confirmed the prediction that Einstein made. So that's how Einstein's theory of relativity started to gain momentum. And you can tell by my example with the ant, that's why it's relative. That's why it's called the theory of relativity, because it's all about how things, motion is only detectable relative to something else. All right. Yes, he was a brainiac. He had barely any formal education as a child. He was considered one of those unruly kids that was going to amount to nothing. Those are my favorites. I tell you what, from my experience as a teacher, it's the unruly ones that show the most promise. I'm glad you brought this up, Bob, because there have been several theories that contradict the theory of relativity. And that's the great thing about science, is we don't stop. We don't say, oh, okay, Einstein was right. Well, he was right about that. He was right about that effect, which, by the way, is called gravitational lensing. And I'm going to do a whole episode on that, because that's really cool, and it's helped us discover some really far away galaxies and stuff. But this experiment showed that Einstein's prediction about this gravitational lensing effect due to the curvature of space was correct. But scientists have then since been trying to, prove or disprove other parts of his theory. And then comes quantum mechanics. Now remember, I said that Newton's laws were fine on a small scale, But if you started looking at something as large as the solar system, it kind of breaks down. The same thing sort of happens with Einstein's theory. Einstein's theory really works in the big universe. Thank you, Bob. Share it out, please. I hope this gets to as many people as possible. Thank you. All right, but Einstein's theory, if you start to look at really, really small, like subatomic particles that are smaller than neutrons and electrons, then Einstein's theory just falls apart. It doesn't work because it's possible for some things to be in two places at the same time. It's possible for you to change something over here that causes a change over here. And we don't understand that, and it drives us crazy. And so the big goal in science right now, in theoretical physics anyway, is to find a theory that combines them all, that reconciles Newtonian, Einstein's, and quantum theory. All of it together they would call that the equation of everything. Or the formula of everything. I can't remember which one they call it, but either way, it's the same thing. When we find that, we will understand the complete nature of the universe. And I think we're a while off. But I love this area, a lot of people have heard of the theory of relativity, know who Albert Einstein is, but really don't know the scope of his work. But when I was doing my research for this, I kept blowing my mind because when you start looking at the geometry, and if you just follow the geometry, it's so weird. Like technically, the past, the present, and the future are the same. Mathematically, there's no reason why we're only observing this point in time. So, but that's another episode. Time. What? One last thing I want to say before I let you go is that I don't want you to go away from here thinking that space is actually shaped like a trampoline with a bowling ball in it. Okay? It's not. Space is not shaped like that. It's just shape is curved in a way we can't perceive. And when objects move through that space, they are following a straight line from their reference, but from the object that is curving the space, they are traveling in a curve. Okay? But it looks the same. We can't tell the difference visually. All right. I think that's it, unless you guys have any questions. The theory of everything. There you go. Thank you, Bob. That's exactly it. Time is an illusion. Bit of a curveball there. I love that. Time is an illusion. Maybe. The deeper you dive into Einstein's theory, though, you realize that when he says that space-time is curving, it's really not space he's talking about. It's time is curving. Now, I don't have time to try to explain that to you, but I will give you a little example. Here's an experiment that you could do if you wanted to. Stand at the bottom of the Empire State Building and have someone at the top. Point a laser up there and shine the laser, wait 5 seconds, and shine it again. All right? To you on the ground, the space-time between those two events is 5 seconds. At the top of the Empire State Building, the amount of space-time between those two events is more than 5 seconds. So the person at the top is going to see those more than 5 seconds apart, even though lasers travel at the speed of light. They're basically instantly there. So why the extra nanoseconds? Because space is curved. The shortest distance between 2 points may not be a straight line. Boom! Alright guys, that is it. I hope that I had 2 missions for today, and I hope I've accomplished them both. One was to tell you a little bit about the theory of relativity so you could kind of understand the beginning of what it was, and 2, to impart upon you, remind you that science is an ever-changing, ever-evolving set of ideas that are designed to be challenged by other scientists, and trying to disprove everything is how science works. So, don't just accept the world as it is. Go find out for yourself. But, remember that sometimes you got to use math to understand what you're seeing. So, you can't always take your word for it. Okay, I mean, you can't always believe your eyes, but as much as you can, try to find out for yourself. Do some research. Just read a little bit about Einstein. And don't forget, I'm going to drop a link to those videos from PBS. I really recommend them. They're great. I would love it if you could support the show. You can become a monthly sponsor for as little as $1 a month at patreon.com/AdamTilted. If you want to give a one-time donation, send it to paypal.me/AdamTilted. Put a note on there that you want to support Orbit at a Tilt, so I can be sure to thank you on our next episode. I will be back next Tuesday, same time, same space time. Well, not really. We'll have moved by then. But anyway, until I see you again, don't forget to look up.